You have to check out, right?
Yeah, yeah. I just like to
That's good.
keep it
Very
light.
good. Yeah.
Because I can't really learn. Well, I mean, I haven't been able to really take in the information for the
Okay,
past
if I
month.
want, can you send me a video?
Yeah, yeah, it's on
I will
YouTube.
let you know, okay?
It's already on YouTube.
You do?
Yeah.
Really?
Yeah, yeah.
Do you have a YouTube account?
Yeah, yeah.
Yeah, you are
Wow.
the physics department.
Huh?
You are the physics department.
Ah, really?
Yeah, yeah. The lectures I upload.
Oh, I don't know about that. I have no idea. Okay.
Yeah, yeah. I'll send it to you on Discord. If...
It's on Discord, I think.
Like, do you ever feel like you're just drowning?
You always have. Are you feeling that way?
Oh, dude. I feel like I like, you know, woke up on shore, you know, I don't know where I'm at. I think I survived, but only barely. I'm trying to catch your face. Trying to figure out where I'm
So, are you running this account?
yeah.
Oh, great.
We are not here yet. Still, we have 2 more minutes.
Oh yeah, no, we can't really.
They are also here.
I shall tell.
No.
Coming on time. Let's get
Hi,
started.
how are you?
I'm good.
And today I will quickly go and finish this spectroscopy.
Excitement.
Then we'll talk about some microfabrication techniques, how to make these devices. Right? So last time we talked about semiconductor, right? So how electrons can move from valence band to conduction band, so depending on direct band gap or indirect band gap, right? So then from that we know how to evaluate the band gap, right? By measuring the absorption. Remember, absorption is given by something like E minus Eg half for direct band gap, and then E minus Eg. Then you have plus or minus that phonon, right? You need to have, in this case, you need to have a phonon to intermediate. So, but this one goes like to square of that one, right? So from there, we know how to linearize it and get that one. But sometimes, so here what really happens, so when you make electron goes here, then you have hole here, right? But we assume these electron and hole are separate, right? But we know this is negative, this is positive. So they always attract, right? So that means they, unless they are, we call this excitronic binding energy. If they are really small, they can separate. Otherwise, they like to stay together, right? This positive and negative. This is what we call the exciton. So most of the time, if you have an electric field or something, these excitons can break. But in some cases, these excitonic binding energies are very large, then they will like to stay together, right? So that's why, like we discussed about the organic solar cells. So their binding energies are very high. They just move as one unit. So other, like silicon solar cells, once you do this one, they are already separated because of that. Remember, depletion region has some electric field, so then they move, right? So these excitons are very important. That's why we remember when we did that absorption, we see something goes to 0, right? This is where we had the Eg, right? So if you take this square of alpha with E, then this becomes 0. This is where Eg, right? So, but if you have excitons, so these exciton energies are small. So if you draw these exciton levels are somewhere here. These are more like hydrogen molecule, right? Exciton is what? One positive charge and one negative charge. That is exactly what you have for hydrogen atom, right? You have one proton and one electron. Then you can use the Bohr theory. Exactly same thing you can use for the exciton. Very simple Bohr theory kind of calculation, because they are very identical. So if you do that one, we know hydrogen atom, we have these states, right? You have ground state, then you have other higher level state, right? You have. Anybody remember this energy? This energy is given by minus 13.6 over n squared, right? So just like that, you have some this discrete states for the excitonic state. So then this curve, usually this is very small. So at high temperature you don't see that very clearly, but if you cool it down, you will see that one, something happening. That is the excitonic peak. You can see here. So high temperature, this is what we exit, this is your band gap, right? But if you go to low temperatures, you can see this peak showing up. So this is exactly the excitonic state. So, because when you, especially talking about these two-dimensional materials, so this light excitonic interaction is very strong. So you cannot neglect this kind of thing. So this is very important to see. So also, since we have these different states like this one, you can see excitonic states coming from n equals 1 to 2, 3, 4 like that. Just like in hydrogen atom you have this Baum series and Fraschen series, how they move, right? Just like that, so you can see excitonic levels coming here. This is very important when you study spectroscopy of semiconductors. Okay, so then, like I said, photoconductivity, we discussed about this one. You know, this is solid state physics. Yeah. Photoconductivity is also another important thing. In photoconductivity, what we do is we just measure the, we know how to measure the current, right? Just apply voltage and measure the, current. So that we call the dark current. But if you can shine light, what will happen? The light can make this electron hole pairs, so that will give you some additional current, right? So that's how we get this, because typically that sigma is proportional to the number of carriers times, I don't know. Conductivity is given by E n times this is something called the mobility. So it is depends on n, right? Number of carriers. If you have more carriers, you have higher conductivity, right? So, but by shining light, you create more electrons and more holes, right? That means your sigma is going to be increased by delta P. So that's how you measure the photoconductivity. So basically, you don't just shine light, we just chop the light. Remember we talked about the chopper? So you can chop the light. So this means light is to this one. During this time, you see your photocurrent is increasing. This time no light, right? Then it is going to decrease. So this is how usually you measure the photocurrent. Very simple technique. You just get a chopper and just measure the current. So you can use a lock-in amplifier or something like that. So next one is, this is actually, you are going to do this experiment in this quantum lab. So this is called the dynamic light scattering, but this is a very important technique to measure the particle size distribution. Suppose if we have some nanoparticles, if they are dispersed in a liquid, so they have different sizes, right? You have some particles 1 nanometer, some particles 2 nanometers, some 10 nanometers. By doing this technique, you can get a histogram. You have this many 1 nanometer, this many 5 nanometer, like that. That's we call the dynamic light scattering. This instrument also very highly used, mostly by chemists, when they use. So this technique is very simple. I think there's a lab in quantum, like next part will be doing labs, right? One of the experiments would be is this basically what you have is in a solution. We have these particles in suspension. So we know these particle, they always go through something called the Brownian motion, right? Particles. So then if you shine light, so say laser light, so then you get what is the scattered light out. So then you have a photo detector, right? That's all you need. So then as a function of time, you just correct this light intensity. So what happens here? So since these particles are making this Brownian motion, so then the scattering changes, right? So you have some kind of fluctuation of your current. So then you can do some sort of correlation. From that you can get the information about the particle size. Very simple experiments. So you will be doing this one in the quantum lab.
Will be something like shining light through milk.
Yeah, exactly. Same thing, yeah. But milk, you don't have big particle distribution, right?
Yeah.
You don't see this kind of curve. Typically, so this is, what is Brownian motion? It's more like random walk, right? It's a dynamic, the diffusion equation.
Stochastic equation.
So stochastic, yeah, it's not deterministic, right? So that's the difference, yeah. So typically, everybody familiar with the diffusion equation, right? So I think this is another thing I think everybody should be aware of. If you have something, second derivative of this one, what is this equation? That's a Weaver equation, right? That's the second order. If you have something like this is just on the first derivative. What is this one?
Diffusion.
That's a diffusion equation, right? So here they both are second order. So here second order and first order. This is a diffusion equation, right? These two everybody should know. So this is basically happening, this diffusion equation. So when you shine light and collect the, suppose if you measure intensity, that intensity is actually kind of random. So then if you have this data, you can do this autocorrelation. Probably everyone know about autocorrelation function, right? Basically what you have is, if you have some intensity at time t, then you look at some time after time, so then you take the average of that one, right? That's basically, you are making the autocorrelation during this time tau. Then you can do the from here you can calculate something called Q. So that's a function of this tau, right? Because this one is basically you are going to integrate, right, over t. This one, right? This one. So if you do that one, it's coming as a function of tau. That is what we are looking at here. This something called G function. So from there, actually here, basically what happens is these particles, they are scattering, right? Everybody remember the scattering problem. If you have something k coming here, k prime going here, difference will be k prime minus k, that is q, that is actually, if k and k prime have this elastic collision, that is 2k sine theta 2, right? This equation, that's what we do in the X-ray scattering, right? So, but we know for constructive interference you need to have this relationship. From there you can get the particle distribution. You will learn this one in the class. It's a very easy experiment, but very useful if you want to look at particles. So once you run this experiment, the computer will give you histogram. It will tell you, okay, this many 10 nanometers, this many like particle size distribution. Okay, so last thing I want to talk about, I think probably we already talk about electron diffraction and things like that. But in many cases, you can use different scattering, electron, X-ray and neutron. So what is the difference? If you use neutron, so neutron is neutral, right? So if you're going through some atom, they don't interact with the electrons, right? So only it can interact with the nucleus. So because typically if you take the atom, you have the nucleus that's with neutron and proton, then you have the electron here, right? So if you have a neutron coming here, there's no effect from electron, right? It's a neutron. Its only effect happens is from the nucleus. So like here, show here. So when it goes here, this electron doesn't care about it, right? It just goes directly. But when it sees this nucleus, it gets scattered. But if you have, so this is same thing, another neutron here. So neutron goes, so doesn't care about anything here except it gets scattered from this nucleus. Because that's mostly magnetic scattering, right? So nucleus has spin up and down, so that means it has a magnetic moment, right? Nuclear magnetic moment. But if you have X-ray, so actually what is this one? This is electron actually. Electron getting scattered already from here. So I showed it wrong. This is what neutron. So they go, if it is far away from the nucleus, goes here, but once it gets close to the nucleus, gets scattered, right? So X-ray also, that is, X-ray is electromagnetic radiation, right? So that can easily interact with electrons. So you can see they have this one, but this is electrons. Electron definitely will scatter strongly with the valence electron. So, but if you look at this scattering, it depends on something called cross section, right? So if it is going through whether this cross section or if it is a smaller cross section, so the interaction. For example, if you have some atom here, if this atom is stationary, if some radiation is going, it has this cross section, right? But imagine if this is like oscillating. If it is oscillating, so then this is your cross section, right? So because it can interact at any point, so then you have larger cross section. If it is stationary, that is only one point, right? So that's why if you have lattice vibrations, you have larger scattering. So if you increase the temperature, larger the vibration, then you have larger the cross section for that. So here you have cross section for neutron. You can see, neutron, they have larger cross section for very light atoms like hydrogen. So they have very large, but when you go to, there's no real dependence with the atomic number or anything. But if you go to larger C numbers, your cross section is going to decrease. But for X-rays, we know is mostly interacting with the electrons. So that means if you have large C, you have large cross section, right? So you can see for X-rays, your cross section with the cross section, it is going to increase. But for neutron, that's why hydrogen you cannot study in other ways, right? It's very difficult to detect hydrogen in like even XPS or X-ray. Anything is very difficult. The easiest way to do is neutron scattering. Hydrogen, deuterium. If you want to study something, you have to do neutron scattering. Please read that one. So yeah, lastly, I want to talk about these four. This is very widely used two techniques, XPS and UPS. So XPS is easiest technique to detect what you have in your sample. It's like a more elemental analysis. Also in what oxidation state it is. Suppose if you have sulfur, you can have maybe sulfur plus or sulfur 2 plus. So whatever that oxidation state, that you can easily observe from XPS. XPS basically X-ray photoemission. So shine light, shine X-ray light and look at the emitted electron, photoemitted electrons. That's what the XPS means. You have your sample here, then you have X-ray source here. You shine onto this one, then what is coming out is the emitted electrons, right? That's a photo emission. So then you have a detector. This is typically this hemispherical detector. That's what I want to show you and take you and show all this equipment. So this detector will collect the kinetic energy of that electron. So if you measure the kinetic energy, then you can get the how the binding energy of these atoms in this material. With each material they have the binding energy, right? So for example, if you take this energy diagram here, this is the density of state versus energy. So you have first you have the co-electrons, right? K, L, M like that. So you have like K, then L1. This is more like K has only S electrons, right? So then L has S and P electrons like that. So if I get the these principal quantum numbers, right? So these are N. N goes from N, 0 is K, right? N1, K, L, M like that, right? So then you have S, P, D, F, that depends on L, right? Second quantum number. So L, this is 1, 2. So N is 1 is K, 2 is S, L, 0 is S, right? S1 is P, like that. So you know these things. So if I look at first, what you have is co-electron levels. So then what you have? After that you have the valence electron, right? Valence is the outermost. So typically, how does, if you take a semiconductor, how things look like? So first I have these co-electrons, K, L, so L can have L1, L2, L3 like that, right? K, L, M like that. So after that, these are the co-electrons. So then we have is the energy. Then we have something called the valence band. Valence band is the outermost electron, right? That's where your electrons can be promoted to conduction band. So in the valence band, we know states are filled up to Fermi energy, right? So if you provide more, then if you have, if you have a semiconductor, what happens? Then you have even band gap here, right? So then from there you have conduction band here. Conduction band. This is your valence band. So I've just drawn it up to this point. So you can see here valence band. So then, so this is for a metal. Here I'm talking about a semiconductor. Semiconductors, we don't have a band gap, right? So if you have a metal, that's all we have. So this is the Fermi energy. If I can have enough energy to overcome the what is called the work function, so then this will be given to the vacuum level. That means the electron is free, right? So even if you have at Fermi energy, that's the highest occupied state, but still it is with the material, right? Unless you give enough that work function, they don't come out, right? That's why come here. But this is, please remember, this is only for a metal. If you have semiconductor, from here, then we have band gap. From band gap, we have conduction band, right? From conduction band, we have the vacuum level. So please remember that one. So in XPS, what happens is, first, with the X-ray, we are going to dislodge one of the electron in the core level. So that has higher cross section, right? So this one is removed. Then what happens? So then the electrons from no, in this case, really what it is doing is this electron will move with some energy, right? That's the kinetic energy. You are not looking, because we are already using X-ray. This is X-ray we are using here. So then it has to first remove this K, or it can even remove some L electrons also, right? So that means this energy should be equal to this. First it has to overcome the binding energy. That means how it is tightly bound to the atom. So then it has to overcome the work function. So if it overcomes, then what will be the extra energy? That's the kinetic energy, right? So it's just like the photo emission, like Einstein's photo emission theory. What do we have? We have this is coming. So then this equal, first it has to overcome the work function, so because we don't consider the binding energy, then rest will be the kinetic energy, right? So just, but here you have to first overcome the binding energy. That means h nu will be equal to, first it has to overcome the binding energy, then it has to overcome the work function, then the rest will be kinetic energy. This is the one we are going to measure from this instrument. So we have this one, X-ray coming here. So then after this one, the electron coming out, we are measuring the kinetic energy of that electron. The kinetic energy is given by then h nu minus EB minus binding energy minus pi, right? So that's what we are measuring. Once you measure this one, we know this one, right? That's the incoming X-ray energy. So then from here, you can calculate your binding energy because pi we know for a given material. So that's basically the XPS results. So usually X-ray comes from maybe aluminum, magnesium, copper. So we know how to produce X-ray, right? Basically, have electron, right? Once you have electron collision, so you excite atom. So then from higher state, so that emits the X-rays. So typically we use like magnesium in our system here. So basically this is what I was going to talk about. So typically if you have, say, this your metal part, so if the electron is coming from this some orbital here, so if it is coming from here to here, then you have this one becomes positively charged, right? So if it is this way, suppose your Fermi energy, so this state is lower, then this one, that means this becomes negatively charged. So that means this is more like some charged dipole kind of situation. So that's why if we have some thing absorbed onto the surface, that so this is coming from the absorbent. Because surface is always, you can have some absorbent, right? So that will change your binding energy. So you can measure. Typically, if you have any sample, if you want to know what is the composition of that one, easiest thing to do is go to the XPS machine and just look at, when you take the spectrum, it will give you all the components. First we do something called the survey spectrum. You are looking at the entire energy range. When you do that one, you will see like everything. If you have oxygen, fluorine, chlorine, nitrogen, sulfur, it will give you this called a survey spectrum. Then what you do is, if you are interested in, say, sulfur atom, just go here and look at this one in detail. So then you will see maybe very nice peak. So actually it may be actually not just one peak, it can be something like that. So then you can deconvolute into like two peaks like this. So then if you do this one, you might see the sulfur coming from K orbital, or maybe coming from S, L, things like that. That way you can get all the information about your oxidation state or which way you have this one. So it will tell you all the information. Very easy technique, right? So, but the only problem is this has to be done at very low vacuum, like 10 to the power minus 10 torr. So that means once you put the sample in, you have to wait about half an hour or so to get enough low vacuum. Then just run the experiment. First look at all the elements you have, then pick one peak what you are interested in and look at in details. Very simple. So here it will show you what you are expecting, right? So these are core level valence. So when electrons comes out, so this is how this is the energy, right? Here I plot it as the kinetic energy. So if anything coming from here, you have pretty low energy. Anything coming from here, that's the highest energy, right? That's the Fermi energy. That will be high kinetic energy. In the kinetic energy spectrum, this will be directly mapped here, right? After here, what happens? Nothing coming out. That's why it's going to So if you have electron coming from here, you have certain energy, right, kinetic energy. If you go here, that energy is little higher. If you go here, that's the maximum. After that, no electron, right? Then your kinetic energy goes to 0. So from here you can directly get your EF. So here you can see for gold sample, you can see gold coming from this PS and all these things. Yeah, same thing. That's the X-ray photo emission. You can do the same thing for ultraviolet photo emission. So this has low energy, right, compared to X-ray. This is ultraviolet radiation. We're talking about maybe 200 nanometer. But here we are talking about X-ray means what? 1 angstrom, right? So that means this has much higher penetration depth. So X-rays can go much deeper into the sample and probe more. But UPS, it has low penetration depth. So, but still they both are surface characterization tools. If you want to see what is happening at the surface, not the bulk. If you want to get more bulk information, you have to do something like X-ray spectroscopy. Right? These are very conventional tools.
Dr. Meany,
Yeah.
3 slides back,
Yeah.
you talked about using a magnesium.
Yeah. Oh, that's for the X-ray.
For the world, yeah.
Yeah. How you make the X-ray? So because typically people can use the target from copper, or because how do you make X-ray? You have some metal. So then you have electron beam, right? So then you excite this state. So then you have some coming down. So then outer ones. That's how you get the X-ray. So the magnesium means your target is magnesium. So then how you get the X-ray? So typically we get X-ray from copper, right? That's the standard. So copper has alpha and beta, 2 peaks. But aluminum, magnesium, they all can be. Only thing you have to do is with the electron, you remove one electron. So then when the electron from upper level drops to the lower level, it emits the X-ray, right? So it can be. But most of the time XPS, they use magnesium X-ray. Copper also can be used. So then OJ process, this is also, there's something called OJ spectroscopy. So, but in this case what happens is, remember, when you remove one co-electron here, suppose this one, so then that electron actually will knock out another electron from this one. So typically what happens when you knock out, if I remove this electron, so then the higher states drop to this one, right? So but this emitted electron, so we think it is just going as a photoelectron, but that also has enough energy, right? That can knock off another electron from here. So that's we call the OJ emission. So there's a spectroscopy based on that, OJ spectroscopy. That's not very common, but people used to get more information about it. You can see here, first you remove this one, so that one will knock off electron from this one to electron. So you can see here what's happening. OJ electron emission. That's a secondary emission, right? Basically. Okay, then I think we talked about this X-ray, electron diffraction and electron spectroscopy. So basically, electron means we have this de Broglie wavelength, right? So that's why we have this diffraction properties. From here, by measuring the distance between these spots, you can get the crystal structure. You can see if you use something like graphene or something, you can get very nice hexagonal kind of structure, right? So then there are we talked about the yields, right? So we have the zero emission peak, so we call the no loss peak, then others coming from other states. Those are some. X-ray diffraction, everybody familiar, I guess, right? So basically you have crystal planes, so then the electrons, the X-rays get in, reflected, and they become constructively interfered, then you can get this constructive, like you can have this Laue pattern or some spectral features. This, I think everybody is familiar with. I think we do a lot of these things in the solid state physics, so I don't want to go too much into that. But this is an easy way to look at the crystal structure in bulk, whether this is a FCC structure, BCC, or hexagonal closed pack, so you can easily get information from the X-ray diffraction. That's something you cannot tell from XPS or anything, right? Because they are surface tools. But here, when you do this, actually Newton also can do that. So, but X-ray is the easiest thing to do. Okay, so I'm going to stop here. These things I can show, all these techniques, XPS, UPS, XRD, all these things in that tour I will show you. So you guys discuss and give me half to 1 hour time, so I will show you all the facilities. So in here I will show you the operation, vacuum systems, all these things here. But this major research facilities I will take you and give you a tour. Usually we do it during the orientation. This time we could do that, right? Okay, so let's talk a little bit about the microfabrication. So this is all used in the clean room facility, right? So I don't know whether you are familiar here. At UFL we have one of the best clean room facilities in the country. This is one of the best, like if you think like Stanford, Cornell, so now we have Georgia Tech, Purdue, and UFL is one of these hubs, so they have MNTC. So this clean room is very versatile, it has all the capabilities. Only problem is it is kind of underutilized because we don't have too many users here, right? So, but it has all the capabilities. If you have any idea, if you can afford, it's a good facility to use. So, first you should know some of the basic things you can do with the microfabrication, these are the things, right? You can have these suspended microstructures. We are talking about the scale of micron or low. Now, with the E-beam lithography, we can even go to nanometer scale. So typically, size feature depends on your light, right? Light wavelength is, even if you go to high UV, it's 100 nanometers, right? So, but if you can use electron to do this one, you can get to nanometer scale. You can see some of the surface machining, bulk machining, you can do these nice features, right? But this requires a lot of processing steps. So that's what I want to quickly discuss about that. Typically, this microfabrication is called top-down approach. That means you start with some vapor, then you do a chin and things like that, and go down to make the your structure, right? Starting from top, go down. So with the nano technology, we go bottom up. So you start with some substrate, we grow nanostructures and do things going like bottom up approach. Here we are mostly talking about top down approach. So you can see some of the features you can easily do with this micro machining. Here we are talking about micron or smaller features, right? We can easily do these things. Most of the features here. So starting with this wafer, silicon wafers, have you seen the silicon wafers in silicon wafers? So typically they come in this kind of crystal. So that's a long process to grow this silicon. So once you get that ingot, you have to slice it, right, to make these wafers. So I will show you some wafers. Also, it depends on these crystalline surfaces, whether it's depending on these are the family of 111 direction, then you can have different crystal structure faces. So typically, when you do these things, you start with some silicon wafer, then we make something called silicon dioxide. It's a sacrificial layer. That's the one we are going to use to make these patterns. Your silicon dioxide is very easy to etch, very controllable way. So then we can have some insulators, things like silicon dioxide is actually insulated, and silicon nitride, those kind of things. So I will show you some examples. So this is typically what we do is we get crystal wafers that you can buy. So like if you get like 6-inch diameter silicon wafer, you can buy for like few, maybe $20 kind of thing. So then most of the time you need to grow a good silicon dioxide layer. So that you can order that one. You can ask them to grow the silicon dioxide to certain thickness. If I want like 300 nanometer thick silicon, you can specify that. They can do it, but they charge for that. But in the clean room, if you have a wafer, you can go and ask them to grow your silicon dioxide layer. And also I can ask them to dice it. Right? You can dice it to, like typically we use like 5 millimeter by 5 millimeter small pieces, because that whole wafer is too big, right? So all these things you can do. This is what I do. Once you make everything, this is called the packaging, is you put it on this chip carrier and do some wiring. Wiring is done by something called a wire bonder. So I will explain that one. So this is how typically ingot looks like once you do the silicon growth. This is a long process. You start with sand and mix with things at high temperature and do that one. So after that, you are going to slice it like this. So then you polish. This is how the silicon wafer looks like. So this you can see this cut here. That tells you the direction of this one. It's a 110 or 100 or 111. So because it depends on, I don't know whether you're familiar with these crystallographic directions, Miller indices kind of thing. So if it is 111, it is more like going across the one, right? So those things are very easy, very difficult to cut in that direction. 100 is very easy, it's this one, right? You can scribe it and then it breaks very nicely. But 111, because 111 direction is more like going across this one, right? That's typically difficult to break. So to grow silicon dioxide, what you have to do? Just simply react with oxygen. You just put your wafer in the furnace, pass oxygen and heat it to high temperature. You can grow very nice silicon dioxide layer. So, but sometimes if you want to increase the growth, you have to add a little bit of water. So then it becomes faster. Here is so typically when you oxidize, you don't put just one wafer at a time, right? You can put like 10 wafers in this reactor, in the furnace, then insert oxygen or water vapor and heat the furnace to about 1000 Celsius. Yeah, 40 and that's it, right? So then you can control the growth time to see if I want 100 nanometers thick, I can stop at certain time, right? If you want more, you can go longer time. That's very easy to do. So then if you want to do the operation, typically in clean rooms they are much more cleaner, so they don't use the thermal evaporation. They use mostly this. Remember we talk about the E-beam evaporator, right? E-beam evaporator means you have your material, so that is heated by, not by heat. They are evaporated by this electron beam. So we shoot electron beam here, and that will heat this one, then it will evaporate here. We talk about this one, right? Thermal evaporation. In thermal, we just heat a boat, right? Passing a current. Here, just that's more clean. Then, so sputtering, we talk about that using a plasma. The casting, so this is called the spin coater. So if you have some thick, highly viscous, we call the photoresist, how do you put a very uniform layer? That's what we call the spin coat. I will show you that one also in our lab. Basically, you put your substrate here, so then we have some kind of vacuum, we call the vacuum chuck. So that will hold that vapor in place, then you rotate it. It's just with the motor. When it's rotating, you just inject your that polymer onto that one. So then it will very nicely, uniformly spread all over the thing. So otherwise you cannot do, right? If you put like without rotating, you cannot make a uniform one. While it is spinning, you just put this one and immediately start spinning, then it will, you can see here. So I just inject with the syringe, then chuck means this vacuum will hold this one in place, then this is rotating. So after spinning, you can see this one uniformly spread all over, right? So this is very important. Very simple. It's only you need is a pump to kind of get a vacuum, then motor to rotate it, right? You don't need any fancy instrument to do that one. Okay, so then when you do this one, how do you make some pattern? So suppose if I need this kind of pattern on this one, these are very small size. So what we do is, first you take the silicon vapor, then you grow silicon dioxide, right? So then we put something called a photoresist. Photoresist is some kind of it's a polymer. So that there are two kinds of photoresist. One is the positive photoresist, one is a negative photoresist. Positive photoresist means if you expose to some UV light, that part, when you put it in a, we call the developer solution, that export part will be dissolved. So it's more like this. So actually in this example I have N-type, negative photoresist. Positive photoresist means, so suppose this is my silicon, right? Then I grow silicon dioxide. So then I put this photoresist. Suppose this is positive photoresist. Now if I expose, because I have pattern, right? So that pattern we make something called a mask. It's a photo mask. That mask has this shape here, right? So if I keep that mask here, like this is open, right? So this is the open area. So now if I expose to UV light, so if it's a positive photoresist, so this exposed area will kind of become weaker. So then if I remove my photoresist and put this one, we put it in a developing solution. In the developing solution, that exposed area will be washed out. So other thing will remain. So that means your pattern, you have already pattern, right? But if it is a negative photoresist, the exposed area will remain. That's a kind of resilient. The other part, if you put in the developer, that will go away. So actually in this example, this is a negative photoresist. You can see silicon, then I have silicon dioxide, then I have this negative photoresist. Now I expose with this pattern. So now if I put this one in the developer, since this is a negative photoresist, the unexposed part will dissolve, right? So you can see right like this. Now, so the reason why we use SiO2, you can easily etch that SiO2. There's something here called buffer etchant solution, buffer oxide etching, BOE solution. So if you put this one in that BOE solution, that silicon dioxide will be dissolved. But in this case, if you put this one, this part is protected, right, with the polymer, that photoresist. Only this part will be removed. Can you see that? So now you can easily remove that photoresist. If you put it in acetone, that will go away. Then what do you have here? That pattern, right? Exactly what you are looking for. But that is something on top of the surface. If I wanted to make this surface etched away, then what should I do? So in this case, you can see the pattern is like this, right, on top of this one. But if I want something carved into the system, I have to use a positive photoresist, right? If I use positive photoresist, what will happen? If I do this one will remain, right? This one will be gone. So now if I put it in the etchant solution, that part will remain, this part will be etched out. Right? So that means you have that pattern carved into the substrate. That's how you make something sitting on the surface or down the surface. So, but this pattern, first you need to have that mask. So the mask in actual clean room doesn't make the mask for you, but if you give the one, so they outsource it. There are places they make the chrome mask for you. So whatever the pattern you need, they will make for you. They are not that expensive. Then that pattern you can use for whatever time you need. Right? So first you need to have the photo mask for that pattern. So here you can see how this one is done. So this is that photo mask. Can you see here? So this is the wave I want. So then with the lens I can, this is the UV light, right? I can focus on this one. Because if you do something like this, you don't make one device, right? It's a waste of time. What we do is, this whole wafer, I dice it into many small pieces. So then that same pattern I can scan, right? So that means at every dice I can have that same pattern because I can raster this one. So then first this part will be exposed. So then when you go to next one, you have that one image. You can see only thing you need is this mask, right? So but when you do this one, first you have to put the photoresist. So after that you do this one. Is that clear?
So the mask is like a mold.
The mold, yeah. So actually it's made from chrome. So it's more like, because what you have is some areas, empty areas, right? If I want some, say this kind of shape, if I want to make, then the chrome, actually they are mostly rectangular. So in that one you have this shape, that is your mask, right? This is empty area. But here we are talking about in micron scale. Yeah, that's the difference. Yeah. That's why they have to do, what they do is they make a picture, then they reduce it and do some processing. So there are companies, they just make the mask for you.
Does mask get smaller than a micron scale?
Yeah. I mean, entire the chrome, the entire whole thing can be as big as this.
Yeah.
But the feature size is so small. Yeah. So this is how the wafers look like. Right? So certain thicknesses, maybe a millimeter, coming from this ingot here. So this ingot, what you grow for months, mostly starting from sand, right? That's how. Here, depending on the different SiO2 thickness, it has different colors, right? This interference. So this is what I was talking about, the spin coater. So you can see this is rotating. So here now, this is how the mass looks like here. Then when you have this mass, then the important thing is the something called the mass aligner. So that's what this machine needs. Because if you want to, sometimes you have to use same wafer to expose to more than one mass. Sometimes people use 3-4 mass. So then alignment is very crucial, right? That's why before you do anything on your substrate, you have to make this something called a fiduciary mark. You need to have this kind of mark. That's the reference. So you always try to align with that mass. So that way we know it is always aligned. So I have some pictures. So you need to have that fiduciary mark on your substrate. So here is what we call the pattern transfer thing, right? Yeah. Here, so you can see this is what I was talking about. Your substrate, this photoresist material, this is the mass you expose. This is whatever the pattern you have, right? So you can see, depending if you have positive photoresist, the exposed area will be gone, right? So if it is a negative photoresist, so unexposed area will be gone. That's the difference. So now you can do whatever you want. So here is with the negative photoresist, how you do the etching. That's what we discussed in that first case, right? You have here the SiO2 layer. No, this is, yeah, you have mass, substrate, mass material, that's SiO2. No, this is just the, yeah. So, yeah, this is a chemistry of positive resist and what is the negative resist. These are the polymer structures. Here, this is what I want to show. This is what I explained to you, right? So this is the silicon dioxide part. So this is the photoresist. So this is, what is this one? This is basically positive photoresist, right? After exposed. Now if I put this one in that BOE solution, that's a buffer oxide etchant, what will happen? This part is protected, right? So only this part will be etched like this. So now if you remove we call that the removal of the photoresist, put it in the acetone, you remove this one, now you have this pattern carved in, right? But in this case, this is a negative photoresist. You can see when you develop, we call this is a developing part. So no, in this case actually they deposit some material onto this one. So like if I want to pattern some gold, so you can put gold here, right? Entire thing you deposit gold. Now if I put this one in the removal, so the acetone, so these things will be gone, right? Because this is going to be removed by the acetone, but this is the metal you get. If you want to make a contact, right? If you want to make a gold contact, so on a particular point, this is how you do, right? After this process, you just put the gold. Is this clear? This is slightly different what I was talking about here. So if I wanted to put some gold like this, suppose suppose on this one I had some material here. I want to put some gold part to connect this one. So how do you do that one? So first you this photoresist, right? So then you expose. So this is now we actually, yeah, this is still with the same. Sorry about this one. So here no negative. These are both positive photoresist. So this different. Please look at this one. So just up to here same thing, right? So here what we did, we just put this one directly into the HL solution. So the what's called this BOE solution. Then we remove the photoresist. So here this is still the positive photoresist. After this I am going to deposit say gold. So when I put the gold is everywhere, right? I just put it in the evaporator and put gold. Now I am going to put this one in the removal, like resist removal solution. When you do that one, what will happen? These things will be gone, right? That will go with that gold. So only remaining part is just gold. This is not negative photoresist, it's the same positive. But in that case, we didn't deposit anything, right? We just etched that one. There are a few steps: etching, lift off, all these things. Now this is what I was talking about, the alignment. See, first you need to have this nice, this fiduciary marks here. So when you put the vapor here, you can see you have to turn it around until they overlap like this. If it is like this, it's not going to work, right? You can make the first time, but second time when you try to do that one, it is no longer aligned. So that's why you have to align with this fiduciary mark just like this one. So each layer should have an alignment feature so that it makes space to the rest of the layers. If you make third, fourth, sometimes you just take one, then on the same substrate you are going to put the second pattern, right? So every time you have to match with this alignment marks. You have alignment marks on the substrate, then you have alignment marks on the mask also. So let me show you one here. Then when you do this etching, also etching is very critical. There are two kinds of etching. You can do something called the wet etching. That means you put it in some etching solution, or you can do dry etching. Dry means you have some gases. So wet etching you can use like potassium hydroxide or something like that. So then dry etching is mostly used in a plasma with some gas, like we can have argon or xenon, any gas like that. So this is a wet etching. Another one is dry etching. This is sometimes called the RIE, reactive ion etching. So that's also sometimes called dry reactive ion etching and things like that. So this is wet etching. So in wet etching, so suppose you have your this one. So you have some thing like this. If I want to etch this one, so yeah, from here, right? So you do this one. This is the whole thing. So suppose this is protected with your photoresist, right? So now if I put this one in BOE solution, so then this is going to be etched out, right? This part, unexposed part. So this is protected. This part is going to be etched out. Like when this happens, for wet etching, it doesn't do very clean etching. So we call sometimes this anisotropic and isotropic etching. Isotropic etching means every direction, doesn't matter which crystal direction, 1, 1, 1 or 1, 0, 0, they etch pretty much equal way. So that means if you do this one, you are going to see this etching happens something like this. So this part is gone, right? You are going to see pretty much like this. This is called isotropy. So that means we call this, so this part we call the, what is called that? Yeah, this length and this length are very different. So no, actually they are pretty much similar. So this is called the undercut, this one. So this undercut and your depth, this is the depth, right? So they are not very different. That's the isotropic etching. But sometimes it can etch like this one. You can say you are almost no undercut, but this depth is much larger. So there's no much control because your directional etching is very different. 111 has certain etching rate and 100 has different etching rate. That's why you have this, because this is anisotropic. So, because depending on your requirement, right? Sometimes people like to have anisotropic etching. Sometimes people like to have isotropic etching, depending on their situation. So this is a dry etching I was talking about. Basically, you put your wafers here and pass your gas here and start the plasma. Then that also do the etching. That etching means it's high energetic gas ions, so that will remove the polymer, right? So here you can see here isotropic etching. So this is what I was talking about, the undercut here. So that is pretty much not too different from this, they're pretty much similar. But in this case you can see an isotropic one, almost no undercut, right? So this your depth is much bigger compared to the undercut. But here this undercut is similar to the depth. So that's why you have this kind of thing. This is isotropic because in every direction that happens. Here is mostly it's only in this direction, right? Isotropic. But this direction you don't have much. Yeah. So in isotropic etching is very simple. You just put it in the chemical bath, right? That's all. If you go to clean room, you can see there's a bay area called etching, wet etching. So that's basically you have this fume hood and this, you can see isotropic etching. Dry, basically put it in the dry area. So this is very anisotropic etching, right? So I'll do this one simple example, then stop there. So suppose if I want to have this design, so this I want to have this circle, and on that circle I will have this kind of thing superimposed onto this one. So I have two mass, right? So then how do I pattern this one onto silicon substrate? You get the idea, right? First you make this open area. So then on that one, this part will sit here with all other stuff here. So what do you do first? Take the silicon substrate, bare silicon. So then what do you have to do? Grow silicon dioxide, right? So that's the first, second step. Here I put like 5,000 angstrom, that means 500 nanometer oxide. That's standard because if you make too thin, sometimes you will have something called the pinholes. If you want to make electronic device, that can short, right? So 300, 400, 500, they are pretty good. So this is now your whole wafer is covered with silicon oxide. Now what do? Next one, I put polymer, right? My positive photoresist. I just put this one, that is red. Now everything is covered with positive photoresist. Now I just put my mask there, right? So this put the mask here on top of that. Then what do? I expose to UV light. So then remove the mask. Then this part is already exposed. This is a positive photoresist, right? Now if I put this one in, so in this case, if I want to have a hole, what should I do?
The dry etching?
No, first this part is now exposed, right? First I need to develop it, right? So that means I have to not develop, yeah. So you have to remove that part. So then, what is that part is exposed with the silicon dioxide? Then I have to etch it, right? Put it in the buffer oxide etchant. So, yeah. So then the exposed resist coated wafer. This is now develop the exposed resist. Develop means you just remove that positive photoresist, right? You already exposed one. Now we expose the subsequent. Now we are going to etch it. Etch means now this is already the photoresist is removed. So now if I, but everywhere else photoresist is there, right? So in this part, photoresist is gone. Why? I put it in the developer, right? But everywhere else, it has the photoresist. Now if I put this one in the buffer oxide etchant solution, this is protected, right? Only this part will be etched out. That's it. So then if I do that one, you have, yeah, that's the, yeah, it can be wet etch or dry etch, whatever you want, right? So here we put it in the wet etch, the DOE solution. So now you have that pattern already, right? The first pattern is already there. So now I can remove the rest of the photoresist. So what is that? That was basically put it in the acetone. Acetone can easily remove this one. So now what do I have to do? Now I have to put that second pattern. So that's actually, you can do it with some metal. Suppose if I want it with aluminum, what I do is, this whole thing now, you covered with, just put it in the evaporator and deposit aluminum. So if we do that one, so start with etch oxide wafer. So now deposit aluminum. So now everything is covered, right? So then I put that second mask. Oh no, after that we put the photoresist, right? So now aluminum, on top of that we have the photoresist. Now put this one and expose to, that's the mask, right? So expose to light. So then develop away exposed resist. So that's only the exposed area, there's positive resist, right? That will be, after developing that part is to be gone. Then after that, you just put it in the acetone and remove that one, then you get this pattern. So these are all what we coated with aluminum, right? So they were like, that's how you do the things. If you want to have a different pattern, you can do that right here. So you can see like, but remember when we went from first one to second one, the mask alignment has to be properly done. Otherwise, this will not be this way, right? Your SCME might be off way, right? So that's why the mask aligning is really critical. Please go through this one, you'll get the idea. So, but still with these kind of techniques, you have to have not very, like if I want to make like few nanometer pattern, you cannot do with this light, right? So in that case, you have to use the E-beam lithography. So that means rather than exposing to this light with the mass, you write with the scanning electron microscope. You have electron microscope, you have to program it so that it can define the pattern. So that's how you do this kind of E-beam lithography. Again, you take the sample, so then you put your photoresist and just do the E-beam lithography. For example, when I did this project, so I had a project with Honda Motor Company, so they wanted us to, actually we ended up making more than 500 field effect transistors using carbon nanotubes. So in that case, what we did was, in this one, we grow carbon nanotubes, like several of these in a given substrate. Then we use the AFM, atomic force microscopy, to image this one. So rest we have to do by guesswork. So when you do the E-beam lithography, you go to the SCM. We know, also we have this fiduciary marks here. That's the one way to do this one. So then, when we do this one, we have to have copy of your image with you. So when you put your photoresist, then with the E-beam, E-beam is scanning electron microscope, you have electron beam, right? That you can program so that I can write one like this and another one like this, so that I can connect with the nanotube. But you don't see the nanotube because already covered with the photoresist, right? So it's a kind of guesswork. So then I can make another one like this. That's why we have several of these. I can write. This is what we call the E-beam writing. So that with the E-beam you can raster your beam and make that. So then after you expose and deposit gold, we have this connected pattern. So then we have to do extra step to make using photolithography to make connection to, because if I have nanotube with this also, you cannot make final connection here, right? To do that one, we need to have photolithography, made large pads here, gold pads. So then you have to make the connection from here to here. So if I have another one, so this is now, these are large gold pads that you can wire easily. So that's how E-beam lithography works. E-beam, we call E-beam writing. So it's not masking. So you have to write these. You can see this is the, maybe your device here connected with some gold here. So these are pretty standard actually, it's not that difficult. Here you can see, so these are the connecting strips. These are done by photolithography. So these writing, these things are done by E-beam lithography, because that you have to do this. You can see these are the photolithography. This is how you, then these things you can easily connect to the outside world. So typically what we do is, if you have something like this, we just put it on a chip carrier. Chip carrier, people have seen the chip carriers, right? So they have this gold contacts with the pins from other side. If you look at this one, you have these pins coming out, right? They can be connected. So then you go to something called the wire bonder. I don't know whether you have seen the wire bonder. It can take very tiny gold wire. You just pick it and just go and stick onto this one. This is how you do. Take the gold wire and hit this one, then go to the other end, hit this one, then it's already connected. So then come here, you hit this one, then go to this one, it's already connected. You cannot even see it to your eye, right, where it's moved. So that's the packaging. So after that one, you can start characterizing the sample. Those are basic things I think you should know how and nanolithography is working. Yeah, here is another one. You can see these are all done by E-beam lithography. So from here you have some micro lithography steps. Yeah, so I'll stop here. It's almost done. Okay, so that's the end of it. So now, let me know a good time for everybody. We can go for a visit and show this facility. Even clean room. I don't know how many people have seen the clean room facility, at least from outside. So tell me a good time, then we can do that. So it is good to see them, right? So here, even if I explain, I don't know how much you can get unless you have.
So we're meeting at 5 p.m. Thursday?
It's 5, then you have class at 5:30, right? Oh, you mean this Thursday? Yes, yeah. So best thing would be
For the
you
presentations.
to email me, or maybe I will have a folder in the Blackboard you can upload to the Blackboard, right? So then I can open from here.
Okay.
Rather than everybody's coming here and opening it, right? So I can have all the presentations open for you.
Good. So 5 p.m. for the presentations.
Yes. So I think you guys can, if I open something, you can upload onto that one, right? Yeah.
Yeah.
Will the formatting change? Like usually Word documents change formatting.
You're not going to do Word, so you're going to do Microsoft PowerPoint.
Might change the.
One thing, no? But have seen mine changing?
No.
Do you want me to just email you? Since
Email, it might be.
I don't have the access to the Blackboard.
Oh, yeah, you can. Oh, you all can email me, that's fine too. Yeah.
For the presentation,
Yeah.
I'm preparing for the atomic force microscope.
Yeah, that's good. Yeah. AFM?
Yeah.
Yeah. So something more than what we discussed in the class, right? Yeah. So I don't want to hear the same thing, right?
Yeah.
So maybe a little bit from your twist.
Yeah.
So you can always get more, because in this class I just gave very surface information, right? So you guys can tell more.
Okay.
Yeah, don't just
Summarize what.
tell me the same thing I told you, right? Yeah. Okay, then we'll see you Thursday, right? Then email me whatever you have. Yeah. But don't take that too seriously. Yeah.
Silicon dioxide is one of the
Yeah.
main reasons that I got like identified out.
I'm
We're going to like see
trying
that
to figure
Yeah.
out
because of the silicon dioxide.
some equations for PowerPoint slides.
Oh.
Because
So
the
silicon dioxide is very
CVD.
amorphous.
Yeah.
They are not
So I'm
crystalline.
going into the math
Yeah.
behind
Remember that they had
how much energy it takes
once they
for
the
Yeah.
the chemical
they
to
had
decompose
a wafer
into the elements.
No, because if you have
But I'm trying to apply it
refractive
to my
contrast is
research.
different, yeah, then you
So
can
I'm
easily.
I'm trying to go deeper than
Because that's all the
I'm
refractive index.
But it's just-
They call it refractive index contrast.
Yeah.
The idea.
Otherwise it's amorphous.
Yeah,
It's
yeah.
no crystallinity there.
What things I can do, I'm talking
For that one, just go ahead and do that.
Okay.
Yes, yes.
Explains
So that-
about
where is